our next speaker, I'd like to introduce Julian, who worked as a research assistant at TU Munich, and then in 2018 joined Fortress GmbH as a research associate in the Research Institute of the Free State of Bavaria for software-intensive systems. I'll let you introduce yourself a bit more extensively if you'd like, Julian, and handing over to you when you're ready.
Okay, thanks. So hello everyone, welcome to my talk. Let me first share my screen. Okay, here we go. Hope that you can now see my presentation. Now it should work. Yeah, right. Thanks for the kind introduction. And yeah, my name is Julian Wörmann. I'm with the Fortress GmbH. I work in the machine learning group. And yeah, I focus on topics like representation learning and yeah, apply them in our industry project, as well as we are interested in fundamental research in our research institute. And the work I would like to present today, named Neural Network and Correlation-Based Earth-Fault Localization utilizing a digital twin of a medium voltage grid. This work has been done in collaboration with our partners at Grid Data, located in Traunstein, also Germany, and our partners Salzburg Netz GmbH in Austria. So today I would like to introduce our approach, our concept to localize earth faults given some pre-generated signatures which were generated based on a digital twin of our realistic medium voltage grid. So on this slide you can see on the right a typical example of an earth fault, right? So you can see this tree touching the overhead line here and so causing an earth fault in our medium voltage grid. And we say whenever some cable, some overhead lines, any conducting material gets in contact with Earth, we have an earth fault, and this is what we would like to detect in our grid. So since in Europe many DSOs, that is the distribution system operators, they run their grids in a so-called compensated mode. So they have a Peterson coil here attached at the primary substation. The grid can be still kept operational during the earth fault. However, it's not in an optimal state, and even the earth fault can cause a second fault that might lead to outages. So there's a high interest in detecting and even localizing these earth faults. Well, detection, it's rather easy because there are some devices at the primary substation that allow to detect the feeder where the earth fault occurs, but localization is difficult. So usually the DSO has to perform many switching steps in order to at least localize the segment, the faulty segment of the grid, and then the let's say true fault detection has been done has to be do even manually. That is, yeah, it's simply based on manual inspection of the cables or the overhead lines to detect or localize the earth fault. Here, we would like to use our approach in order to yeah, localize these earth faults more efficiently. Right, and we would like to do this based on existing measurement hardware that is already available in these grids. So we would like to use the power quality measurements at the primary substation in order to localize. Here you can see an overview, schematic overview of our approach. That is at the top right here, we have a measurement of our earth fault in our grid. And then, as I said, we would like to compare this measurement with signatures which are stored in a pre-generated database. And we do this based on a digital twin. That is, we model our grid. You can see here on the left, this is a MATLAB Simulink implementation of this grid. So we model the power source, we model the transformer, everything, the lines. And here we are able to artificially inject earth faults at some locations and so generate our own signatures that we can use for comparison. So another approach would be that you simply wait for true measurements and store them in a database. However, this can be very time consuming. So here we follow the approach of generating our own signatures and use them to localize the earth fault. This can be seen here at the bottom. You have here the standard sine curve, and then at 10 milliseconds the Earth-Fault occurs, and you can see here the blue phase, that is the faulty phase. The voltage drops to 0 in this case, and this is the signal we would like to use in order to compare the signatures from different locations, and so to localize the Earth-Fault in the true grid. And as I said, here we focus on voltage signatures, and we even only take the faulty phase and store all these signals in our database. So what are the contributions of our work? Well, we were able to design such a digital twin of a real-world grid, and we were able to inject different Earth-Faults with different characteristics at different locations, and so to generate a huge database that we can use not even for comparison. So this is the second contribution. We could even use this database in order to train a neural network. So if we simply wait for true Earth-Faults, that will take some time to get some measurements here. We are really able to generate our own training material, and so to train a neural network in order to localize the Earth-Fault. And in our evaluation, we compare this neural network approach with a, let's say, standard parameter-free correlation-based analysis, where we simply calculate the correlation coefficient between the true measurement and our signatures, and we compare this to our neural network approach. And even better, we were also able to get true measurement with true known locations, and so we could assess how this approach that we learned on this artificially generated training data, how this approach transfers to the real scenario, and if we are really able to localize true Earth-Fault events. So on this slide on the right, you can see an overview about the grid that we model in our evaluations. So in total, we have 86 different stations or nodes given here, and at each of these stations, we generate Earth-Faults with different characteristics, that is, different Earth-Fault resistances. So the overall grid here is a radial feeder with several branches, and you can see here in the middle you have let's say big branch separating into two different branches or feeders, and the whole grid is a mixture of earth cables and overhead lines, so realistic grid. Then in our experiments, we observed that it's beneficial to not only generate one signature for one node or for one Earth-Fault resistance. It's better to have two different databases. That is, one where the Earth-Fault occurs at the peak level of the voltage, as you have seen in the previous slides, and another database where the Earth-Fault occurs close to the zero crossing of the phase. So we have two different databases and use them to localize. So how do we do this? What is our localization approach? Well, in our experiments, we model the localization as a classification problem. That is, we would like to predict the node ID we have seen before. We have these 86 different nodes, and we would like to predict the node ID and so assign a node ID to the signature or to the measurement, and so to localize this measurement. As I said, we use a correlation-based approach. That is, as you can see here on the right, we use a time window of these signatures and measurements. So here in red, you can see the signature, and in blue, that is the faulty phase of a true measurement. We use this window here in order to compare and calculate the correlation coefficient between these two signals. And furthermore, as I've said, we use a neural network-based approach, and in the neural network-based approach, it's a little bit different. We do not compare to all the signatures in our database. As I said, we use this data in order to train our neural network, and then the neural network simply maps the input to a probability distribution, and we can simply assign the node ID based on the highest probability in our output layer, and so predict the node ID and localize the measurement. So here you can see the first results. So as a proof of concept, we first evaluated the whole approach based on our synthetic results or synthetic measurements. That is, we are simply or purely based on the digital twin. That is, we generated signatures with different fault resistances and simply left out one of these fault resistances as our testing data. And so we have 86 different signals that we would like to localize. And here on the right, you can see the results. On the one hand, we have the top 1 accuracy, that is simply the average over all these 86 different nodes. And you can also see the top 3 accuracy, that is the accuracy if we are able to predict the true node ID, at least in the first top 3 nodes. You can also see the root mean squared distance measured in hops. That is simply distance between the different or the predicted and the true node ID. What we can see here is, well, for the 2 data sets, the peak and the zero crossing, and also the 2 methods we evaluate, that is the neural network and the correlation coefficient, especially for the top 3, we were able to predict the true node ID in the top 3 in more than 95% of the cases. This really shows that these signatures are kind of reliable and that we can use signatures in order to distinguish between different grid positions and locations. So this is simply our proof of concept that we can use this digital twin approach, these artificially generated signatures for localization. Now, the interesting question is, can we use these trained models or the data we generated in a real-world setting? And in our work, we were able to assess this and to evaluate if we can really use this to localize true Earth-Fault events. So in our setting, we have Earth-Fault events at 2 different locations. You can see here, we have location 59 and location 6. And we have different realizations of these measurements. That is, simply we run this experiment 3 times in the case of location 59 and 2 times location 6. And the M3 is highlighted here because for M3 we use the zero crossing database, whereas for all the other measurements we use the peak database in order to do the comparison. For the results, we here also give the distance in hops between the predicted and the true fault location, and we also give the top 3 node IDs we predict with the different methods. And you can see for the true measurement M1 and 2, we were able to really predict the true node ID, or at least in a neural network case, to predict a node ID in the close neighborhood of the true node ID. And also for M3, we were still able to do a pretty good job here and are close to the true node ID. Unfortunately, the performance drops if we look at location 6. So, well, for the very first measurement here, the neural network was still able to kind of predict the node ID in the neighborhood, but for all the other cases, the performance significantly dropped, and we were not able to localize this measurement. So what's the reason for that? Well, simply, or we assume that simply because of how we generate this Earth-Fault. Well, for location 59, we simply switched one of the phases to 0. So we have a almost zero fault resistance, whereas for location 6, we try to generate the Earth-Fault based off a grounded copper wire that we moved towards the phase, and so even created a lighting arc. And here we have kind of varying fault resistance during the Earth-Fault, and this is still difficult to model. And here we still have things to do in order to better localize these Earth-Faults. However, very promising that we could use these models and the data we have artificially generated, and we could show that we can even transfer this at least partly to localize true Earth-Fault events in a real grid. And this is also the conclusion of my talk today. Well, in our work, we could show that we have this proof of concept that we can use this data and localize Earth-Fault, that we have signatures that allow to distinguish between different locations. And we've even seen that we can use these signatures to detect Earth-Faults in real grids, so we can transfer the learned model to a real scenario. What is the future work? Well, we have to analyze further what are the influencing factors. So maybe we need to enlarge our database, get more signatures with different parameters from the grid. So simply information that might not be accurate, and so generate different signatures. However, this is not a big problem because the calculation of the correlation coefficient, this is very efficient, can be done in a few seconds. And even if we have more training material, the training of the neural network would be offline. So if we apply the neural network, the computation time should be still the same, even if we have more signatures during training time. And then, as I've said, we have seen in the real scenario that there might be some different scenarios according to the fault resistance. So the fault resistance is currently the only parameter we have in our database, the varying parameter. Maybe here we have to evaluate if we could model a varying Earth-Fault resistance during the fault event, and so have other signatures that better reflect these scenarios in the true event of fault in the true grid. So that's our work. So thanks for your attention.
Many thanks, Julian. Really enjoyed your presentation. I see we've already got a hand raised for the Q&A. Maybe I'll hand over to Wörmann for a question.
Thanks, Elizabeth. A question, I mean, what I'd like to continue the issues you raised yourself. First of all, if you have fault location and mediation should be done very quickly, right? Typically, this is a high request. So how quickly can you be with your databases and neural network processing to be effective in order to mitigate fault effects timely enough?
Well, currently for the localizations can be done in seconds. As I said, we have for the neural network, the training time, but it is completely offline. Sure, if we change the parameters of the grid, have some new switching states, we would have to retrain the network, but currently this is not a big deal. And if we are still able to, let's say, separate into different feeders, I'd say this can be still done in a very little time, that you can efficiently calculate the correlation coefficient and even efficiently train the neural network to other switching states, for example.
Yeah, I mean, I don't see the training and offline part as critical, but the online part to be fast enough in order to be responsive and then take actions. And the second question somehow related to this. So I think it's kind of well known that low impedance faults are relatively easy to handle with. So the question is, how effective are the neural network approaches as compared to the more traditional approaches? Because, as I said, low impedance faults are relatively easy, but the high impedance faults are what matters. And there, I don't see the results as of yet. So what do you think? Can you give us some idea about towards high impedance faults and how you'll be able to deal with that?
Good question. Well, it depends. So sure, with our digital twin, we are able to generate all the different scenarios, and this is definitely one scenario we have to investigate further. It depends if we could really show this in a real grid. So we really need the data from the real grid. Fortunately, we have also access to other grids and other DSOs that will provide data to us, but yeah, we still need this data and even need the information about the let's say the structure of the how to say, the scenario of the Earth-Fault. I'd say based on these synthetic results, we are able to generate these Earth-Faults and investigate how the neural network performs in this scenario. I'm not really an expert about these grids. I don't know how often these high impedance faults occurs. But sure, this should be also investigated further, and how in these scenarios, how our approach transfers to these maybe more realistic scenarios. Yeah.
Okay, thanks.
Please put your hand up or post a question in the chat if you have another question. If not, I'll pose a question while maybe you think about it. So my question comes, I suppose, like the methodology that you used for doing the calculations, particularly if I put my utility hat on, when we're looking at fault currents and things just generally and modeling them, the system was highly unbalanced in the subtransmission distribution area, where previously like positive sequence impedances, negative zero sequence impedances were all sort of standard, I suppose, for understanding fault currents and signatures. So I was just curious, like, did you look at unbalanced cases and the impact of having an unbalanced system in terms of impedance unbalance as well as load imbalance? Or was this considering sequence impedances for the analysis?
Mm-hmm. Yeah, thanks for the question. Well, what we did is we did some kind of sensitivity analysis, that we changed some different parameters of our grid and tried to get a feeling about what are the most important parameters of our grid that we need. And as I've already mentioned, maybe from our DSO we do not get very accurate data, or even some missing data. This is what we have to investigate further. We have done this for a very small grid in the past, but we have to extend this to these more realistic grid scenarios, and let's really see what are the factors that we need. And as I said, maybe that we even enlarge our database and account for all these different facts that we are able to generate these signatures, and hopefully they really show the right behavior that you also observe in the true grid. But this is also could be also future work, that we investigate all these different parameters and how they affect the signatures, and maybe lead us to enlarge our database.
So another follow-up question, unless someone's got their hand raised, I don't know who might. So the next question I had was, I seen that you had 2 locations in the analysis of taking data input. And from experience with SCADA data, it's not GPS time synchronized, and it can be reporting really erroneous timestamps. And so I was just curious, like, how important was that time synchronization of the data to look at your correlation and your, I'll hand that over to you.
That's a very important point. This is also what we observed, that sure, due to the, or depending on the location in the grid, we have some time shift in our measurements. And this was, it's even current work that we try to investigate the impact of these time shift or delay of our true measurements compared to our signatures, how to deal with this scenario. So we have tried different things, like we align them with the peak value or the zero crossing of the signature and the true measurement, and try to get the best alignment. But we still observe some differences in the results if there's no or if there's some difference in the alignment. So this is still an open question, and still not completely solved yet. It's currently based on a threshold simply, and maybe this can be also done in a more effective and efficient way to get a better alignment between true measurements and the signatures.
Interesting. Thank you so much. If there's any other questions, feel free to raise your hands, or maybe go over to the Slack later on if something comes to mind. But thank you again, Julian. Really enjoyed your presentation.
Thanks.
Wonderful. And so